Okay, so it's really important. One of the really important principles in quantum mechanics and in physics in general is that whenever we have a situation that we understand, a simple situation that we understand very well, we want to use our understanding of that to generalize to more complex cases. This is what we're doing here. We study the one-dimensional potential well, infinite potential well, very, very carefully, very, very thoroughly, and so now we don't have to go through all the um, detailed derivation anymore of the solutions for the three-dimensional case. We can use our understanding to generalize. Okay, um, so let's just briefly consider an example um, where we have. Let's just plug in some numbers for the box. So let's assume that the box has dimensions of 1 angstrom in the x direction, 2 angstroms in the y direction, and 3 angstroms in the z direction. Okay, so if we plug in the ground state energy, which corresponds to all the quantum numbers nx, ny, and nz equal to 1, then we get from looking at this this form for the energy, we want to square both the quantum number for each direction divided by the length for each direction, and so we use that for 1, 1, 1. We get 1 squared over 1 squared plus 1 squared. That's the quantum number ny squared divided by 2 squared. 2 is Ly. Okay, and 1 squared over 3 squared, and when you add that all up, which times pi squared h bar squared over 2m, when you add that all up, you get 49 over 72 times pi squared h bar squared over m. Okay, it's not obvious which will be the first excited state. Okay, because since we have different dimensions for Lx, Ly, and Lz for the sides of the box, then it's you don't necessarily get. It's not as easy to predict what the next value is, but what we can show is that if we make since the longest box dimension is in the z direction, then and since the eigenenergies are proportional to 1 over that dimension squared for each one of the different directions, then we can understand that if the denominator of one of these is big, like it is for LZ, this is the biggest, we get 9. Since LZ is equal to 3, then LZ squared is equal to 9. Then an incremental increase in the quantum number corresponding to that direction is going to have the smallest effect on the energy. Okay, so if we increase the quantum number in the z direction by 1, we go from 1 squared to 2 squared, or 4, and so this gives us the smallest increase in the energy from the ground state, and what we end up with is 61 over 72 times pi squared h bar squared over m. Okay, so then what's the next one? Well, we can imagine we sort of have two choices. We can increase in the z direction again from nz equals 2 to nz equals 3, or we can increase the next largest dimension. We can increase the quantum number in that dimension by 1, so we can go from ny equals 1 to ny equals 2, and it turns out that gives you the next one, the second excited state, and when you add that up, you get 76 over 72 pi squared h bar squared over m. If we increase the quantum number in the z direction by another one, up to 3, and we decrease the quantum number in the y direction back down to 1, then we get 81 over 72. So here are the first few, if I did the math right, here are the first few energy levels. 49 over 72, 61 over 72, 76 over 72, 81 over 72, 88 over 72, and 108 over 72. Now, of course, I can actually simplify these further, but I left them this way just so that it's obvious that they increase in energy. Okay, and again, a general principle is that the direction with the longest dimension, in this case the z direction, has the smallest incremental increase each time that you increase the quantum number, and so that helps.